Since competitive networks measure the difference between the input and weight vectors, it's worth spending some time considering how to set up the initial weight vectors, as this obviously has a great effect on the network's performance. Some implementations of competitive networks set weights randomly in a similar way to a backpropagation network, and this certainly works, but it's perhaps not too transparent in its operation, given what we discussed in the last video. Another method might be to set the weights randomly, but then normalize all the vectors so that they have unity length, that is, a length of 1 unit. The best way of illustrating this is by example. Suppose we randomly obtained two weights of 0.1 and 0.9 to a 2-input neuron as shown on the screen. Now these two weights make a vector of length or magnitude of 0.1 squared plus 0.9 squared all square rooted, or 0.906. We could normalize this to have a length of 1 by dividing both components by this length. The first component is 0.1 divided by 0.906, which makes 0.11, and the second weight is 0.9 divided by 0.906, making a weight of 0.99. If we followed this procedure for all the neurons, then we'd have normalized the weight vectors to unity for each one. I should emphasize though, that although I'm doing this to show you a logical training scheme which makes sense in the light of what we discussed in the last video, there are other training schemes which don't normalize the weight vectors like this, and in fact these other schemes are more common. If our chosen training scheme didn't preserve the length of the new trained vectors after training, then we could also renormalize them like this in the same way. The initial distribution of the vectors is also worth considering. This is important because in competitive learning, different patterns fire or activate different neuron vectors. Obviously, if we set all the vectors to random positions, there is a chance of them clustering in unfortunate ways, as shown in the diagram on the screen for 3 2-input neurons. Here, neuron 3 would move towards input 1, but neuron 1 has a long way to go to move towards input 2, and neuron 3 may actually be closer anyway, leading to poor learning as neuron 3 is eventually torn between moving to input 1 or input 2. Neuron 2 is closer to neither and is stuck in the middle. So you can probably see that you might be better off distributing the neuron vectors evenly as shown on the diagram on the screen. Although I haven't seen any particular evidence that this is a more effective strategy than choosing the vectors randomly, you can probably imagine that it could be. And you could also combine both approaches by having some neurons chosen at random and others evenly distributed.